Okay, thank you everyone. My name is Charles, and as you can see in the title, although it's titled Reverse Engineering Agentive Control, I think we're still pretty far away from actually reverse engineering it, not to mention engineering it in such a way that is based on a sophisticated understanding of human or animal agency. But however, I do honestly believe that there is a theoretical framework and that which has the potential of providing a viable solution to reverse engineering agentive control. And so in this presentation, I aim to bring forth such a control theoretic framework under which we can study the physical implementation of agentic control by taking physical measurements in the brain of the brain's electrochemical processes and building towards the phenomenological sense of agency. So I'm here to basically advocate for bringing back dynamical systems and bringing in control to systems neuroscience, in particular to neuropopulational activity. So first, I'd like to talk about that. Say that testing causality can be hard in the real world. No one system, as we know, is isolated, and no two components are completely unassociated, except for obviously the ideal case. So I think any physicist would probably agree with me on that, and there is always back action when one system exerts influence on another. And I agree that in most cases in engineering, we can add in nonlinearity and gating effects and take care of that. But in practice, we don't always have to worry about feedback. But in more complex systems, which is the case for most natural systems, this effect becomes quite intrusive to our investigation. So I think consistent with this idea, it has been generally difficult to directly observe causation in the brain, but I think we don't have to worry. I'll talk about how feedback control theory can help mitigate and untangle that intricacy. And next, from a philosophical point of view, I think to gain a further understanding and to allow analytical and computational studies of agency, the discipline needs a quantitative characterization, a measurement of the degree of agentive control that can be implemented in the brain. And I think with refinements, control theory has the potential to provide such a measurement required to describe agency. And then last but not least, I think people in different fields are starting to do things and think about things in a similar spirit. But we need a common tongue to interface between philosophers, scientists, and engineers. I think, for example, philosophers often talk about multi-level motifs, self-reflexivity, attention, and so on. And while engineers are building robots and systems that are multi-layered, self-recognizing, and attentive. So in the section sizing up the control architecture, I will develop further on how our theory can help the many ideas converge. And I'd like to also mention that compatibility, I'll try to make it a common theme throughout the talk. And the first compatibility statement I wish to make is with regards to computational functionalism. I think that our control theoretic framework is compatible with both the proponent and opponent arguments for computational functionalism. I think this framework directly deals with the physical implementation of algorithm and provides a substrate neutral, not substrate independent characterization. And finally, whether a substrate is deemed suitable to implement our agency depends on the specific physical process that we deem finally, eventually relevant to the phenomenon. And so let me start by giving you a brief introduction to the theory. So why dynamics? I think so. Dynamical systems comes from physics, and physicists think about the time evolution of the physical world as governed by a set of dynamical laws, expressed typically in differential equations, and well, which stems from obviously empirical measurements and our knowledge based on in physics. And so any physical system basically is a dynamical system in some sense, and it naturally flows along a trajectory in the state space, which is also the desired solution of our mathematical model. So I think if you believe in physicalism like I do, I think it's safe to say that dynamical systems are never completely wrong. However, you may ask, why not just consider other computational models such as a neural network? Indeed, I think they can be very efficient and for the sake of computation and application. But typical computational models are created to optimize for the input-output relation, and which is can be sometimes independent of the physical relationships inside the system, which is also why they often lack direct interpretability. So again, the dynamical system approach directly builds on physical knowledge and measurements, which allows us to generate a biologically grounded model of what the brain physically is and how it is physically implementing agentive control if it is. Ideally, a dynamical system also permits state space realization, which is a schematic of the state space and on the right side of the three-state system, and which this will open up a kind of delicious worms to allow for the analysis of stability, robustness, and eventually controller design. And so let me give you a little example. This is the Fitz-Hugh-Nagumo model of a neuron, and stemming from the squid giant axons. So as you can see here, this is a two-state model. It has a V and a W, V with V being for the membrane potential of the neuron, and W is sort of an umbrella state variable for all the other recovery dynamics that the neuron has. And so this provides a mathematical formalization of the neuronal dynamics in an essential way, and you can visualize the flow of the system starting from a point after a period of time. You will know that the system will end up in some other state. And so on the left side, this is the flow of the system of the Fitz-Hugh-Nagumo neuron. And on the right side is the velocity of dynamics. And further, you can find out where the system's equilibrium is. So at which point it is at equilibrium and ideally will remain there forever without any interference. And you can also dig deeper to analyze for the stability of the equilibrium by linearizing it around the system. So as you can see, the linear system is exponentially stable, so we can know that the nonlinear system, which is the Fitz-Hugh-Nagumo system itself, is locally exponentially stable. And further, you can also add in control. And this is basically the central idea of model predictive control. You can the Fitz-Hugh-Nagumo neuron gives you the model, the math for how the neuron will act, and you can basically exert any form of control you want, and you will be able to somewhat predict what the like neuron will act. So in this case, I'm injecting a constant current input, and as you can see, the neuron goes away from the equilibrium and enters into this stable periodic orbit, which corresponds to a constant firing of the neuron. And so why why do we want to add in control? As I was showing you earlier with the physiological model, control basically gives you the ability of adding in some other systems interaction with the current system that you're looking at. So a system's current state is described by a state vector x, and the measurement determines the length and the values of the state vector. And control theory directly deals with the mathematical structure of a state space, which comprises all possible states of the system. And in control engineering, control is the artificial input to the engineered system designed to drive the system to some desired state by the use of algorithm and feedback. But yeah, so as I introduced earlier, physical systems are intricately coupled and with one another, and their dynamics can influence each other in very different ways with delays, of course. So how would you crisply describe causality in this case? If you do experiments in a system, not just the brain, in any system, you might find yourself perturbing one node or one state such as the neuron from earlier, weakly, and you'll get a exponential decay back to the equilibrium. But then if you perturb it large enough to reach a threshold, it will suddenly start oscillating for a long time. And in an ideal model, it might not just, it might just remain there forever. And all that is to say, with adjustments, you can get switching or thresholding or oscillation or almost infinitely any other behaviors from just a graph, even simpler than this. And so, well, typically from something like this. So I think this also relates to how physical systems can perform logical operations and digital computation. So feedback systems theory provides the means to circumvent the formulation of the causal structure of agentive control by basically funneling down this architecture to a closed loop map to give you the prediction that you will want. And so now, what if we don't have a good enough understanding of the entire system, of both parts, of both blocks? So what if we don't know what we don't know? I know this sentence sounds trivial, but feedback control theory does let us deal with something like that. So the problem of having unknowns. And so all you have to do is to adopt a slightly modified view of the configuration on the left side, and to model the dynamics of the part that you know, and then model the dynamics of the part that you know and design the part that you don't know, that you don't know, like an engineer. So there are tools in optimal control that, based on mathematical optimization, can give us a closed form expression of the controller subject to constraints. Or it can also tell us what is infeasible if your constraints are infeasible. So by solving for example, an LQR, a linear quadratic regulator, for example, or by some other forms of model predictive control, infinite time horizon, you can get an optimal, in theory, ideal controller of what you can take, which you can take to compare with the actual physical system, the physiological measurements from the brain you take, and use that information to determine whether your controller design is good enough, close to reality, or if you need to add in more constraints that should also be based on your biological or physical knowledge. And that's how I think feedback control theory allows you to translate from physics or biology to determine the controller that you want. So now, how does this theoretical framework connects to the agentive theory? Now, we have to get one assumption straight, which is that we assume agency to have a physical embodiment. It can lie in a specific brain region, or it can be distributed across the whole body, or it can disseminate into the whole world, in which case it might be trivial to talk about agency anymore, but I think it has to be somewhere to be found, and therefore it has to be explainable by physics. So I think the current mainstream belief in neuroscience for where agency might be is probably the brain. And so people who use control theory to study neuroscience typically consider the brain as something equivalent to a microcontroller. Like a digital computer on an airplane, or something on an integrated circuit. Something that is packaged and sitting on top to implement some control policy that is that nature somehow engineered into the brain. So for example, a PI controller, which is a parameterized controller, can well capture the control dynamics of the through flight. And I think if there is agency, this line of thought will say that, oh, this is what agency looks like in the brain. But I think we shouldn't stop there. I think we want to understand the physical implementation of this kind of agentive control, not just an algorithm. And so I think one promising place to look at this is in the electrical activity of neurons. And so I think you have to think that the brain is a physical system doing complex computations, relying primarily on the electrical activity, which enables fast and rich information communication and processing. It might also, to some extent, and perhaps to a greater extent in smaller brains like the fly, that it also relies on the biochemical activity and signaling. That is what is doing the computation, not completely digital in the way that our laptops are, but as a physical system, it is doing some sort of computation like that. And so when you're studying the control of behavior like this, you are using measurements of the mechanics of behavior, the speed, the velocity, the angular velocity. And so the controller that you design or that you reverse engineer out of these measurements are going to be a controller over the mechanics. But we want something that works in electricity or biochemistry, basically. So we want to move the lens into the brain and actually measure the electricity. So in a separate line of research, people focus on the neuropopulation activity, where they measure the electrophysiological, where they use electrophysiology or calcium imaging that are fast enough to basically take measurements of the electrical events in the population of neurons. For example, this is an experiment of a mouse sitting in its homepage, facing a male mouse sitting in the homepage and facing a male intruder, and it's going to exhibit some sort of aggressive reaction. It will begin by some low-level aggressive state. It will start by also exhibiting milder aggressive behavior, such as sniffing the intruder, versus as time progresses, it will begin to exhibit more and more aggressive behavior, such as directly attacking the intruder. And this is a gradual increase in aggression, which also corresponds to the population in a hypothalamic nuclei activity. And so with a algorithm that is called RSLDS, a recurrent switching linear dynamical system algorithm, we found that there is an approximate line attractor corresponding to the aggressive state. So when the mouse is less aggressive, the population activity starts from one side of the attractor, and as the aggression increases, the vector slowly progresses along the line to the other side. And so it looks like a knob of volume that you can turn up for the aggressive state. But what we really want to understand is what is the hand that is turning up the volume of the knob for aggression. And so, and I think that is what agentive control, I think by taking measurements of the electrical and biochemical activity in the brain, you'll get a further understanding of how physically the agentive control, the invisible hand, can be implemented in the brain. I guess we'll have to skip this part. But what I'm trying to say is that we have a new theoretical framework coming up. Well, it starts from the distributed control of power grid, which is a large network. So basically, this allows for the concatenation of multiple of this configuration into a larger network, and it will it's called the system level synthesis. It allows you to re-parameterize the overall larger system level behavior, and allows you to implement controller design over the larger system. And so I think it naturally leads to two dimensions of describing a complex system, which is layers and levels. Layers are dynamical systems that interact and are coupled together, and they influence each other. And then levels are basically dynamical systems of dynamical systems. Any component is a dynamical system, and any dynamical system is a component of a larger system, and that is levels. And finally, I'd like to point out a few directions of how this theoretical framework can be compatible with other theories of consciousness. For example, active inference has to do with optimal control, and predictive processing can potentially be explained by model. Predictive control basically maybe perhaps some part of the brain is evolved to have a model of the other part of the brain, and it is basically doing a prediction of the dynamics of the other part, and it's therefore implementing control based on its model. Yes. And finally, thank you for your attention. I'd like to thank my two advisors, David Anderson and John Doyle, who gave me the inspirations. And here's my email if you have any further questions or thoughts on that, please shoot me an email. Thank you very much.
Okay, so we have a few minutes for questions. Who wants to go first? Okay, I'll be asking first.
Okay.
I'm a big fan of control theory.
Okay.
I'm a big fan of agency.
That's great.
But exactly. So this room has a thermostat.
Okay.
This room is running a PID controller on that thermostat.
Okay.
Almost guaranteed.
Okay.
Does this thermostat count as an agent?
Does this thermostat count as an agent?
Like, I want to know, like, you can do control theory on a lot of systems, and I want to know if you believe that all systems over which I can do control theory are agents, or if some of them are not.
I think in some sense you can claim that it is an agent. It just very, well, compared to our understanding of our agency, it is very simple and tractable because we designed it. So maybe we don't actually think of it as an agent, but maybe it has agency, and maybe, but most likely you will have something that is of a very different form as we do, or as a biological neural network does. Yes.
Okay, then I'll be asking a second.
Okay.
Again, I like agency and I like control theory. So you had a slide where I think you were saying agency as, let me see, I wrote it down here, as electrical / chemical activity, and agency as something else. Yeah, as the mechanical controller. Yeah, this slide, yeah.
Okay.
So, what is agency here? So there are people that are doing optimal feedback control in motor neuroscience. That's basically the only mathematical framework we have nowadays.
Yes.
Motor control, right? I can understand if you said the brain is a controller. I'm not sure I would agree, but I could understand that. What is agency? Like, you want to link it to the physical world?
Yes.
What is agency?
What is
agency? Link it to the physical. Because this slide is about bridging physical measurement to agentive theory. What is agency in physical measurement?
Well, I guess what I'm really trying to say here is what do we determine as the physical implementation of the phenomenological properties of like having agentive control in ourselves. And if we take measurements of our behavior, then as I was saying, the controller that we get out of these measurements are going to be a controller over our behavior. Well, yes. So the state variables will be the mechanical states, and so the controller design will be a function of these mechanics. But then, if we move into the brain, then we look at I was in this slide I was building towards how I think it is implemented in the brain as electrical and biochemical activity. And if we take measurements of those physical states, then we can get a new understanding of how it is being implemented using, in these physical states. Thank you.
Okay, good time.
So maybe like
yes,
money already probably something, but what do you think about when I hear the word controller? It's always controller needs some kind of set point. There's already the goal in it. As you said, some strategy designed by humans, it's human determined fix the goal. What do you think of when you say agency? Do you think it's important to have like a self determining goal? System is safe. Set the goal, for example.
System is safe or
System itself has its own goal. That kind of intrinsic.
Yes.
I think not required here.
So I think this is it can be accounted for in some degree by the part I couldn't really develop further on, but I think this multi-layered and multi-level design could help account for that. So these layers can be layers of dynamics that are fast or slow. So the slower dynamics could be systems that are optimizing around basically longer term goals, or this is also similar to the idea of active inference in the free energy principle framework. And so these fast and slow, the short term and long term layers can also influence each other, and these interactions in between systems can be thought of as control in some sense, right?
Well, let's think later. Thanks, Kingston. Yeah, Kingston, please reach out to translate that. Okay. This mic doesn't like my voice. I'm probably too loud. Right. Let's thank Charles once again.